Hello, everybody. I hope you are all well and healthy. This is lecture 3. In this lecture, we're going to be talking about object files, compiling C and assembly file, and talking about the linking process. So you are all familiar with compiling a C file. In here, you have your test.c program. Use a compiler in Linux called GCC, and then you produce executable from it. Let's see what happened once we are using the GCC. Basically, what is happening before having executable file at this point. Is there anything before this process? Okay, once you compile a C file, before producing executable, the system basically produces the object file for you. But you don't see this step if you don't specify an object file option in your GCC command. Once you got your object file, then the linker gonna be used to link the object file with the library files to produce your executable. These are the steps here. So use the compiler to produce the object file, and then at the same time you gonna be having some libraries which you need to link them together and then produce your executable. These libraries basically are the include file at the beginning of your C code. For example, when at the beginning you say $, include stdio.h, that's the file, that's a library file that you are calling. So the linker at this point calling that function and integrate it with the object file from your C file, and then integrate them together and produce the executable at this point. Modular programming in C. Basically in C, you can divide a complex C program into multiple files or multiple modules, and then you can basically create object file for each of these modules, and then you can link them together with the libraries that you have been using, and then at the end you produce the executable file. If you have gone through previous labs and exercises, by executable we mean the binary file that is produced at the end of this process. If you don't give it any to GCC any option, it produces a.out file file for you, so that you can run it in Linux command like this. So you have done this in your lab before and you're familiar with the process. If you're looking at the process from high level to level hierarchy, in between object file and C file, there is other process that's happen automatically when you use GCC compiler. So once you use the GCC compiler, it produces the .io or object file for you. How assembly programming lies in this hierarchy? Basically, assembly programming is between your C file and your object file, meaning that you could have your .asm file produced from your C file, and then you could generate your object file from the assembly file, and then you could link them together, and then you produce your executable at this point. So object files are machine codes plus some metadata uh, information. When these metadata are the unresolved symbols, when you link them with the library, they're going to be a resolved symbol. For linking and uh, debugging, we normally use this object files. I mean, this metadata from object files. So for more information on object file, you can visit this website. So we don't uh, go through the detail in the object file produced from assembly or C file. It is just enough for us to know the process and how assembly compared with the object file in this hierarchy with the C file and object file um, places. So it is live in between the C file and object file. And then we have different object file format. So we have common object file format, we have relocatable object file module format, and then we have executable and linkable object file format. So this is the one that we are using in this course. We basically tell the GCC compiler to produce ELF type object file for us. You will see this in the next few slides. So how is the process of producing executable from an assembly file? So this is simple. So you have your assembly file like test.asm in here. Use your assembler, not the GCC, to produce your object file. And then from there, use the linker to finally produce your executable. That's a simple process. So on Linux, how we can go through this process of producing executable from assembly. This is simple. For 64-bit machine, so if you have your file name first.asm, use NASM, the assembler, to produce the object file for you. So the output of this command gonna be first.io. first.o. And then you link it with the libraries using ld command. So this is your first.o file that you obtain from here. So then you put it in here, you link it, and you finally got the a.out file from this step. And then you run it and you get the output of your program. So the steps are illustrated in this figure. So you have your first.asm file, you use this command to get the object file, you get your object file in here, and then use this command to get your executable file, and then you run it simply by saying ./a.out. So as explained, we here produce a binary executable for a 64-bit machine. So that is an ELF 64, meaning that, okay, if you want to produce me an object file, produce it for a 64-bit machine. And then you link that, and then you give me executable for 64-bit machine. But if I want to produce that for 32-bit machine, so because 64-bit binary will not run on 32-bit CPU machine. So how we can produce executable for a 32-bit machine. Here we have the process. So first we use NASM to produce the object file for 32-bit machine using this command. So the output of this command on Linux is gonna be first 32. Oh, note that our input file to this command is this one. So we assume that we have an assembly file written with the name first32.asm. So we apply that command, apply this command nasm on this file to get the object file in here. And then in here, we link them with the libraries, but note that at this point we have ELF underscore I386, which is uh, another synonym for 32-bit Intel processor. And then you get your binary file and finally you run it. So the steps are again illustrated in this figure. So let's now take a look at an example of how a C program can be compiled into object files and then from them producing the binary executable. Here in this example, we have two files. One is test.c, another one is fact.c. And basically in this program, this is our main program. We define the function factorial at the beginning, and then we have our main function. We declare x as 8, and then we print the factorial of 8 in this program. Here is our function, and our function implemented in different C file, fact.c, and here is how we implemented this factorial function. Now we're going to show you how we can produce the object file for each of these files and then link them together to produce the executable at the end. Here's the illustration of how we can do this process. So first we have our test.c file. We use gcc minus c option test.c to produce the object file, the first object file. Note that previously when we wanted to run a C file, we didn't have this minus C option, right? Because we didn't want it to produce object file and we wanted just straight ahead produce the binary file, but here is different. Since we want to produce the object file, we need to use this minus C option at this point to get the .o file. Otherwise, the program gonna produce a binary file for us, and since some of the functions are missing in here, the program gonna complain. So the process is not going to get through. If you use gcc on test.c, it's gonna complain about the factorial function that is missing. So in this process, then we have factorial.fact.c. Then we again produce object file for that using this minus c option, this gcc command. And then we have our library files where we can link all those libraries using this single Linux syntax. So we have ld, I guess this one is dash dash dynamic linker, and then you give it the these library names, and then these are your object file, and then after your object file, then you're gonna give another library to the command. So once you enter, then it's gonna be producing the executable for you, which is gonna be in this case a.out at this point. As you can see from the previous illustration, the previous slide, the process is a bit seems a bit complex for linking stage, for LD stage, if you look at the previous slide. So to make it easier, we can use GCC to automatically get all these required library for us and link these to object file with the library and then produce the executable for us at this point. So as mentioned here, GCC gonna runs LD with appropriate argument, meaning that it gets the required library automatically for you without you determining those libraries. That's the way to simplify this process. Okay, this is a summary of compiling C file to 32-bit applications. For this process, we need to install side libraries in our Linux environment. So we need to install these 3 libraries, and if those commands work, that's fine. But if not work, you are probably missing this library, and you have to install this library as well. This is sudo apt-get is the command just if you type it on the Linux terminal, it's gonna install the library automatically for you. So to be safe, just install the 4 libraries in Linux so that you don't get any error regarding missing libraries. Okay, so the previous process that we explained about producing object file and binary file for the example test.c and factorial.c was for a machine with 64-bit CPU processor. But what if we want to produce executable for 32-bit machine? This is how we do it. We add one option called -m32, meaning that, okay, produce object file for a 32-bit machine for me. So again, you have -c option in here. You get your object file, then you have your library file, and this is the way that you run your linker. So you need these libraries, and then you have your input file, and then this. So all of this is only one comment. Is one Linux command all with all these arguments. So you put it there, and then you enter, and it's gonna give you a dot out. So there's a way to simplify that process as we explained for 64-bit case. So here you also can use GCC to do the linking process for you without having all those arguments in your Linux command. But because it is a 32-bit machine, you use GCC -m32 to produce a that out that run on a 32-bit CPU. All right. Our second example gonna be about an assembly program. So how we can do the process of producing object file and linking for assembly files. But before we go to that process, I want to briefly explain about the macros and function that is available for us for debugging purposes from the textbook that we have in our syllabus. So these are the macros that we can use. So we have print integer macro, print character macro, print string macro, print null, read integer and read character, and dump registers that we're going to be using to get the value of all registers within that program. So this is the call function, meaning that you can use that call function to get this macro running. So, and how we can use this, basically, so whatever you want to print out as an integer, you put it in EAX register. So once you load it in EAX register and then you call this print function, then the value of that integer gonna be printed out on the screen. So here we have print character, right? Then if we want to print that character, before we call this function, we need to load that value in AL register. So we put it in AL register, and then we call print character. Then we have our character print out on the screen. we have also macro print string in here. To print out a string on the screen, you need to give the address of the first byte of that string and put it in EAX register. And then there's still gonna be a null terminated string, which is like a C string that you guys are familiar with. So once you call this function, then the machine gonna be printed out the string that's stored in the memory with the starting address that is already saved in EAX register. As simple as that. So print a new line characters, meaning that you have printed an integer on the screen and you want to go to the next line. You use this print underscore NL simply, and you can go to the next line. Then we have the read integer character. Read integer character gonna read an integer from the standard input, which is your keyword, and store that value in your EAX register. So once you call this function, you're gonna get that value stored in EAX. Then you can use it in your process or in your code. Then read character is for reading an ASCII character from a keyword. So basically you read that from the standard input and store it as ASCII value in AX register. We have another macro in the book that we can use, and that's called dump registers. And there is one argument in here, which is num. Num can be any integer numbers. It's basically tells you where this dump register used in your code. For example, you could have a long code and then you want to print out the value of registers within several locations in your code. So you can start by naming the num from 1, dump register 1 means that it dumped the register at location 1. And then you can say dump register 2, then it can print out the value of the registers at location 2 in your assembly program. As simple as that. All right, now we are familiar with these macros so that we can use them in our assembly program without knowing the detail of each macro. As you will see in this course, writing this macro need a bit of knowledge in assembly program, and at this point we just use this macro from the book and use it for mainly debugging purposes and communicating with IO peripheral. So later on you will see how we can write our own macro like print integer or print character or read string or print a screen. You're gonna be seeing this almost at the end of the course how we can implement our own macro in assembly program. All right, let's now focus on our assembly program and how we can have a program that's a mix of C and assembly program, and still we would be able to produce an executable for this program. You guys might be familiar with high-level languages like C, C++, Java, and you kind of might have not seen an incorporation like assembly file in your C or C++ code, but it can be done in practice. So meaning that you can have your C file and then your assembly file. For code efficiency, you prefer to write part of the code in assembly, and then you're gonna integrate them together and produce the binary at the end. So we explain this process. We assume that we have driver.c file, and then we have myprogram.asm file, and this is some library assembly file. Then to create the binary from these 3 different files, mix of C and assembly, this is the process. We produce the object file from each of them, and then we link them together to produce the executable at the end. That's just as simple as that. So since we can produce object file from the C file, so we go to that process. Then we can produce object file from assembly file. That's good. We do that too, and then we get that object file from another assembly file, And then we link them together to get the executable. This is as simple as this. Um, to produce the a.out file, and then we just run this file for us. So let's take a quick, closer look at each of these files for a simple example. This is going to be a simple template that you're going to be using throughout this course. So let's go through them and see what they are. Um, all right, so before taking a look at these files, so there are some things that you need to do on your Linux machine to be able to create those object files and then link them together. So the steps are given in here. So basically you first need to install NASM. This is a command for NASM. Simply install that. And then you can download those files from the text book that we introduced in our syllabus. So there are some example in there. So you can download those files. And in this example, we are interested in these files. So we need this file. So you can take this one from the book website. I think I have also this one incorporated in Lab 3. So if you want to go to the process one by one, it might be convenient just to go through Lab 3 to do this process. And then for compiling, we use NASM function for this. And this is our include file for the assembly. And then we create a file named driver.c. So as I said, all this process clearly has explained step by step in one of the lab, which I think is going to be lab number 3, so that you can go through those lab, go through that lab and go through the steps one by one. But here I briefly explain the process for you. To create a file, driver.c which is simply calling your assembly function, you can write something like this file. So this is our driver.c file that we use. So it is as simple as this. And then you need to have this file also in your current directory to be able to run the program. So as I explained earlier in the stage of this lecture, we need these 4 libraries to be installed in our Linux. This is also explained in lab number 3. And then we can use gcc command to produce a 32-bit object file from driver.c. Okay, and this is how our myprog.asm look like. Basically, you will be given a template like this, and then this is your template, and then you put your code in here. So don't worry if you don't know the meaning of this command at this point. So this syntax is going to be explained throughout the course, but initially we're going to be using this template, and as we go, we're going to be understand what the meaning of inter push a, pop a, leave and return is. I will be providing the skeleton file for this one in the lab number 2, so that you guys can just take it and put your code here and use it. For this example, it is just simply loading number 100 to EAX register, number 20 into EBX register, and subtract them and print the result on the screen, print a new line, and dump the value of the register at this point of the program, and we are done. So this is the program that we're talking about. This is our driver.c, as simple as this. And then these are the steps to run it. We use NASM to create the object file from myprog.sm, and then we link all these together to get the binary file, and this is the command for it. And then we simply run that command using this. So I collected all these syntax in one page so that you can see all of them. This is an illustration of the process. You GCC to get the object file from the driver.c. You use NASM to get the object file from this assembly file, and then use this command to produce object file from this assembly file. And then once you have all this object file, you simply link them together, and don't forget to put -M32 to produce a 32-bit binary file for you. So this is the program that we're talking about. This is the driver.c, and these are the steps that we've gone through, and this is the output of our program. So basically 100 minus 20 gonna be 80, and then you dump the register value at that location, in this location in our code, and these are the value for the registers. For example, AAX has this value, EBX register has this value, ECX has this value, and so on. And we also have the flag registers that the value is 206. So I collected all these commands in one slide. So all these commands, you can put all these in a shell file, and then you run your shell file. The good things about the shell file is that you don't need to, when you want to run your file, you don't need to write all of this on this the terminal. You just simply call your shell program to run all these commands for you. So this is also part of lab number 3, if I'm not mistaken. Maybe it's gonna be number 3 or number 4 lab. So this is your shell file. Let me explain about that. So this has to be -O. Okay, you use NASM to produce object file for this one. And then this is to have your AND, meaning that, okay, I have another command to run. So it's then what is the other command? Is GCC -M32, which is for 32-bit machine, and work on driver.c to produce driver.io for me. So then the shell gonna go execute this one, and then goes to the next line, and then next line, which is we have AND here, right? To this time we said NASM -F elf $1.asm. So I'll tell you what $1 is later. And then you GCC, link them all together, $1 driver O, $1.o asm underscore io.o, and we finally run $1. Okay, so basically when you want to run your program, you give an argument to it. So this is how we run the program, right? It's a run.sh argument, myprog argument. Myprog is coming from, so we assume that the input file to this program, to this shell, is myprog, and it is myprog.asm. But when you call it in this format, you don't add the .asm file. Do not add that, otherwise your program gonna get error. So this is gonna be your argument. In shell, you can have multiple arguments to your file. So shell knows the first argument as $1. So whatever you put in front of your run.sh, you're going to have multiple of them. So in this case, we only have one. So shell knows this one as $1. Take this value and store it in $1. And if you have another argument, you take it and put $2, and so on. But since for this program, we only have one argument, it assigns it to $1. And it assigns it to $1, and when it wants to run this one, right? So $1 gonna be replaced with the argument that you give it to the shell file. So basically it's gonna be nasm minus f elf. Instead of $1, it's gonna take myprog and put it in here. So it's gonna be myprog.asm. So basically it's gonna be produce the object file for myprog. I'm gonna be myprog.o. In the next line, GCC gonna be linking all those files together. And here you can see $1 minus O $1. It means that it's gonna produce the output with the name myprog. And then what are the input argument? The input argument, it has to be O. Driver.o, $1.o, $1.o is myprog.o. And then we have asm underscore io, which produce in the previous step its object file. So we use this GCC and then we get the executable. As we mentioned, the executable name gonna be myprog. Why? Because we use minus O option to tell him that, okay, this is my binary file output. And then you say dot slash $1. So the next command that shell gonna run for you is simply $myprog, which is the binary that you produce at this stage. And it's gonna run it for you. You're gonna get the same result. This is part of the process in lab 2. You go to the process, and if you have any question, just post it in the discussion forum of this lab in Canvas. Then you can also write your own program in our template. As I said, so this is a template that's given to you as a scale.asm. So you can put your own program in here to simply run it with in conjunction of C program. This is the end of lecture 3. If you have any questions or concern, please post your question on discussion forum in Canvas, and I will be responding to those questions. See you on next video.